It was a component version of a perceptron. So it is capable of doing localized regression for linearities automatically and doing it adaptively. The argument at that point in time was it can solve complex systems, complex sets of equations completely on its own. It must be like human level intelligence, right? So they were anticipating and predicting that neural networks were just like the brain, and they developed a brain system. When they found out what it could actually do, and they started sealing out on what they were capable of developing with respect to the hardware and software limitations of the time, the chilling effect was brutal. It wasn't until actually the late 1980s, early 1990s in which neural networks actually came back. Okay?
Oh, wow.
So they weren't feasible during the time that they were originally developed. And it was the concept of this mechanism for gradient descent and the simulated annealing we talked about, where we artificially increase the learning rate occasionally. Effectively, it's saying how much of the gradient I'm going to take in at a given moment. How much does the local approximation help inform me about what the space is around me? That is an argument for effectively the ruggedness of the surface that is described by the reaction and relationship between the weighted elements. So the next step of the process was actually that simulated annealing idea, where we artificially adjusted those back-propagated weight systems. So we started being able to do this in digital computing. We started thinking about it from the perspective of a surface and high dimensionality. And the interesting part about this is characteristics of the weight look a lot like a ball rolling down a surface, right? We talked about this analogy beforehand. So if I calculate the gradients of this surface, it runs in the opposite direction. It runs the weight, or this particular theta here would be reduced in this case, right? I have to reduce the weight to go up, right? So if I reduce the weight, I get max gradient. So if I take opposite gradient direction says this weighs down, right? So the very first moment, the very first, I guess you say moment as in a movement based upon a characteristic of external force, is going to be that the gradient provides a forward momentum towards the direction of maximum increase. So we say the real movement and the gradient in the initial case should be matched, right? Whatever the gradient is times whatever the actual learning rate is will be the amount I move. Now, I end up in a new position as a result of that movement, right? And I'm kind of on flat land now, right? So what's happened? The instantaneous calculation of the gradient, not so great. So knowing that this flat land is likely going to stop at some point in time, that's the argument within most gradient spaces, is that the answer usually doesn't lie in a wide area of multiple possible solutions that are equivalent to one another. It's usually like the best compromise is a balanced state. So currently we say we're on flat land. So what we're going to do is we're going to take the gradient. You notice the gradient of this surface is tiny. It's not very steep, but we were already moving, right? So let's conserve some of that energy, momentum. We're actually going to model the construct that we keep some of the gradient from the previous epoch, from the previous generation. We keep some of that one and add some of the new one together. Yes?
Is that like a fixed value that you keep of the previous gradient, or does that depend on the previous gradient?
It decays.
Oh,
so
okay.
Effectively,
so
we want to say something like, it'd be like, I don't know, 80% of the learning rate based version of the gradient from the previous estimation. This is like how the decay is effectively modeling friction.
Okay.
So it would be related. You can do this a lot of ways. That's the answer. You can do this a lot of ways. It depends on how much you want to try to exactly model the characteristics of gravitation, friction, and inertial and momentum characteristics, right? How exact you want it to be and how your objective function comes from the idea of creating this propagation of forward movement is I keep some of this, right? And I use some of this.
Right.
So the knowledge of how I was moving beforehand was effectively a ratio of how much I got in terms of gain in performance right? Effectively, how much I reduced my altitude in this case would be the drop, and then that drop and forward momentum would encourage more momentum conversion, right? There's several versions of these.
So it's more fluid than
It's more
just-
fluid. You can do it however you like. Similarly, to remember how we talked about the idea that you can create an objective function, a variety of different objective functions. How much of what kind of error and how quickly are some weights in some places being updated. All that stuff can be based upon a different set of metrics. We did RSS, MSE, we talked about cross entropy. All those are mechanisms for calculating a type of error within the system. So if you remember that all of the different types of error we could calculate with respect to the classifier, any of those errors are also valid for creating either penalties or objective functions for reducing total error in the system. This particular one just happens to be the one, or a mechanism, a one version of a mechanism, where we have taken gradient descent and we've added on this idea of momentum. So there are other ways to do it, right? So there's actually one called ATOM and ADA backprop, and they utilize stronger versions of this decay gradient, but also have the idea of simulated annealing. So the inertia decays, and when it decays to a certain point, you flick it, right? That's the other portion of it, right? So if it decays too much, you hit it anyway. So that's the idea. We move forward. Our real movement is the product. We get stuck in a local minima, right? We know it's local because we know the global's on the far side of the graph over there. So this is the cool part about it. Even though the gradient is 0 here, there's still momentum. So if we move forward with momentum, we conserve the original energy. We can actually get ourselves back out of this particular segment. Ultimately, it slows, right? Because the gradient is now running in the opposite direction of the desired momentum. So what's going to happen here is a product of this system. If momentum is enough, it's actually going to get us over top of the hill, but then we're going to start on a new gradient process, right? We're effectively going to have to learn what that surface is, because we're going to have to conserve new understanding of the new instantaneous gradient on that surface. It's not going to stop at the edge of the hill. It's just going to have more of the energy is going to be coming from the new gradient on the far side of the slope, and there's going to be less total conservative energy from the previous momentum. You can just kind of close your eyes and imagine a ball rolling down a surface, and that's the reason why this works and why it's such an effective tool, is because you can imagine it, thus you understand kind of how it works internally. The more you understand how these things work, the better you can create something that works with them. The more obscure and obtuse they are, the more it's like, I don't really know what knob I'm cranking, right? But now I know what this concept of momentum is, right? I can effectively crank down gravity a little ways. I can crank down friction a little ways. That makes the momentum conversion stronger, right? The momentum conservation stronger, right? Which might make the ball roll further around. But at the same time, it might make it accept and then reject several local minima, right? It might fall into it temporarily, but still keep rolling. The idea then would be that you'd have to sort of spend longer time rolling around and around and around and around until you finally came to a stop at the bottom, where the momentum was not capable of bringing you up out of that big gap. The argument being that if you get all the way to the bottom of something approaching a global minima, it'll be very hard for momentum to bring you back out there, okay? Yeah, this is a conversion of kind of an idea we've been talking about previously in 2-dimensional and 3-dimensional space. You have global minima for this whole total system, but we remember that the weights for the values in this case are randomly initialized, meaning I can start from anywhere. I can either be dropped down here in the global minima, really lucky, right, or I can be dropped up there at the global maximum. One at the global maximum, depending on where I end up on either side of that global maximum, is going to have 2 different paths of gradient descent. This is the reason why I said previously these things will not converge characteristically to this ideal outcome in any given circumstance, right? Every version, every time I drop it, if I drop it slightly over here, I go down this one. If I drop it slightly down here, I go to this portion, and then finally drop into the global. Right? Both are minima with respect to wherever the initialization started. Think about this as a complex multidimensional surface, right? We head over here into what it looks like in 2D, right? And we have all these other strange relationships where the concavity of the local minima makes a difference with regard to the inertial characteristics of that gradient descent with momentum. So a lot of times if it's very narrow, deep and sort of wide slope, it's going to be hard to get enough momentum to get out of it. But if it's a very narrow and not super deep, it'll be easy to escape with momentum. But the idea also infers that saddle points, right, if you try to use simulated annealing and you happen to be on the far edge of the system, right, if you're over here in the bottom of the saddle point and you shoot off with some increased value in that direction, you'll actually end up behind the mountains and often in an area that doesn't provide you with any good minimums, right? So now you're going to be behind the mountains, you're effectively stuck on some planar surface. It's going to take you a long time to find your way back around, right, to mine back through, yes?
So do these get complex enough where we're dropping multiple balls at the same time and?
You're always dropping multiple balls at the same time.
Okay, so it's not just like.
This one? This is what these look like. This is just two weights. This is a simulated surface.
So each weight is its own.
Each weight is its own space, right? So let's look at it, rather than being the change in the weight relative to the change in the error surface is now the upper dimension, or loss is the upper dimension,
Okay.
right? So now we have weight one with respect to weight two. So not only are we making adjustments for minimization with respect to a singular value, but they interact with each other, such that one weight, one value, and then another weight and another value can be a minima for that specific local space. So what does this look like in higher dimensions? No one knows. Okay, we have no idea what a bumpy surface like this looks like in 10D or 20D, right? But if I make the argument to you that this system will be conserved, and we look at this idea, right, that the gradient, the Jacobian of the surface is always going to provide us with a vectorized normal of maximum increase, right? So this vectorization says normal to the surface, I have a maximum tangential interface that will always provide great positive increase in the current function. Now how is this calculated? This is calculated as the instantaneous gradient for all relative regions around the interface, right? Effectively just a little bit all the way around, interfacing that, and then telling me which direction out of all of those directions I could go is most up, which is the greatest increase or positive value output of this particular surface. Any of you guys seen Ender's Game? I don't know if I mentioned to you guys beforehand this idea, but Ender's Game, right? How do they determine which way? So you're in 3D space, right? You don't have that idea of projections, right? Valuation. So I like to say this is like Ender's Game where it says the enemy's gate is down.
Zero gravity for those who.
Zero G, yeah, zero G space, right? So the reason why is because it's effectively higher dimensionality, because without gravity, we tend to think in 2D, we're planar, right? So our brains are built planar. So in Ender's Game, they're trying to figure out how to fight in zero gravity in space, right? And so they have kids that are learning to fight each other. It's a really weird book, but it's that they fight each other and they have a gate on the other end, and their goal is to get through the enemy gate in order to win the scenario, right? So one of them comes up with this idea that the enemy's gate is the down direction in order to try to create a value of pursuit that makes sense according to their traditional 2D perspective, right? I say the enemy's gate is in the opposite direction of the gradient, right? The enemy's gate is negative grad. That's the direction we want to go in, because it doesn't matter how many dimensions it's in, as long as we're going in the opposite direction of grad. Even a high dimensional vector, guess what it is? It is always going to be the best high dimensional vector to solve that system such that it will be the maximization of conservation from loss. We know loss is the opposite of what we want, so we want gain, so max gain is negative loss. Max loss is positive grad, so whichever way is down, right? So whichever way is down. I think it's funny because of the fact that once you kind of get that in your mind where you say, I don't have to understand it, I don't have to be able to visualize it, as long as I trust the process, that if it works in 1D and it works in 2D and it works in 3D, right? It should keep working in 4D, even though I can't really draw it, and 5D, etc., such that similarly to naive Bayes, right? Naive Bayes was able to solve the problem by decomposing complex interactive systems by assuming them to be relatively independent. There's a certain assumption of independence with regard to the calculation of these instantaneous gradients. But the relationship is that eventually, once all of the worst offenders have been minimized, right? Even though we've maybe been moving the gradient around, characterized based upon the worst offenders, once they start to reach some form of local minima, we can start cleaning up the remainder of the error that might not have been as easy to propagate to some of the other smaller weights in the system, right? So we start off with everybody attempting to get some form of their participatory error, and then as we converge minimization of error, some of those, basically who the worst offender is going to change each epoch, or should, right? So you have a high gradient, I'm gonna move based upon your high gradient, I'm pushing you way down. Now all of a sudden you're making less error, right? Now all of a sudden you've got error and you're pushing down. That's where I'm looking at it and saying everybody's sort of pushing down the highest mole, right? Pushing down whack-a-mole, right? Till everybody gets down and you start to be able to get things to where effectively they're going towards zero in terms of error. All right. We've talked about this. This is just another version of it. If you want to look at it with some of the update calculation rate, we utilize the term alpha as learning rate here, but we can use lambda or nu. There's a lot of different ways that it can be written, so I like to try to show slides that have it done all the ways it can be seen. Unlike traditional ML, where there's kind of like one way that it seems to be done in pretty much all spaces, since neural networks were devised and developed by like 3 different disciplines kind of in conjunction with one another, mechanicals were involved in the development of the mechanical adjustment systems for the interface control. They tend to use alpha. Computer science tends to utilize nu, and electrical engineering tends to use lambda. So depending on where you're at and what they're applying, there can be slightly different notation for the concept of learning rate. But notice, the thing you're going to notice is that whether it is theta, whether it is omega, or whether it is w, which those are all versions of weights as well. Weights can be a lot of things, right? We use beta in our textbook and some of our stuff. We use beta for the coefficients, right? There's no difference between a beta and a theta, and an omega and a w. They're all the same thing. They're all just values of weighting. They're all values of coefficients for scaling. So we're saying the coefficient is adjusted by subtraction of the opposite of the learned rate of the gradient L here. This is the gradient utilizing that stylized L, which often implies the Laplacian. The reason why Laplacian is because it's saying I'm taking the partial differentiation of contribution of error for the entire set of weights, and I'm saying that there is an ideal theta, right? So ideal theta in this case saying there's non-zero but target error level. Okay. We've already talked about this, but I want to cover it again just briefly because now that we've had a chance to really look through it, we talked about the universal approximator capacity of the neural network. Effectively, I can model any relationship of a system by recombination of these linearities and then treating each of the outputs of the linearities as a feature to the input of a subsequent system, right? So the output for one neuron becomes the input of the other neuron. If the output is technically, then becomes a feature. So I detect a feature and I pass that feature off to you. So do several other people pass their features off to you. Then you detect a pattern in their features, and then you pass on what pattern you detected from their features. So these systems, any given relationship of elements can be modeled by changing the number of hidden elements within the layer such that we can create more and more complex surfaces, more and more complex descriptions of how the items or how the elements of that feature are distributed within that particular space. Then I can actually sequence this, right? I can pass that understanding of the space off to another neuron that will solve yet another problem with another feature or recombination of sets of features at its level, right? Further and further abstraction from the original system of information. The hard problem here is two things. Adding enough flexibility in order to be able to model really complex systems causes danger of overfitting. The neural networks are super prone to it. We have a lot of tools we try to use to avoid it. We talked about some of those. But the other problem here is that the wider the network gets, the less sort of relevant amount of the individual error can be assigned to that node and weight. So the gradient, vanishing gradient problem, right, as it backprops further, individual contribution gets harder and harder to understand and harder to differentiate. So wide networks, relatively shallow, relatively wide networks, suffer quickly from vanishing gradient problems. And we utilize different activation functions in order to try to compensate for this. First one we've discussed is sigmoid. Everybody remembers sigmoid because it is our traditional discriminant function, right? So I said previously that that neural networks themselves are integrators and discriminators. This is the element where I discriminate at the end of the aggregate or this summation, right? So I sum it and then I run it through this activation function. So what is this activation function modeling? Saying sigma here, right, similar to our logistic function. We call this the logistic function. That at some value 0 within this system for the value with respect to x, we would have approximately 50% chance of being either activated or not activated with respect to neuron. That threshold, right, we can set that threshold somewhere in this system such that we say, well, this might as well be a 0 or this might as well be a 1 by the time it gets to this point. We effectively do that with respect to the input values by adjusting the coefficient characteristics of the natural number, right? Natural number e to the negative x raised here. If I change the adjustment of that linearity, I can do what? I can change the steepness of the slope of that, and then I can shift it forward and backwards by a specific amount. I'm basically adding that 1 to it in order to compensate for the problem that we end up having, which is a negative and a positive portion of the natural logarithm here, because I want to have it be with respect to, or an assumption of, a probability distribution, saying that this now becomes, the output of the neuron now becomes a likelihood estimate, right? It's vote here. If it was on a committee, every individual neuron says either I'm sure it isn't, or I'm sure it is, right? Or it can provide around the center of the distribution value, right? It can provide degrees of certainty. Say I'm 73% certain, or I'm 34% certain, right? Degrees of activation then become more of a modeling of the release of neurotransmitters in the neurological system. If any of you understand that idea, great, I'm glad. You don't have to in order to get this, but since neurons can't partially activate in a biological system, they either fire or not. The only way that we can simulate the actual true interactions between neurons don't actually send electrical signals to one another in real biological systems.
They're chemical, aren't they?
They're chemical, right? So the electrical signal causes the release of a little bundle of neurotransmitters. Those transmitters are released over the gap between those two spaces, and the concentration of which arrives at the postsynaptic neuron is the degree to which that neuron becomes activated by that particular state. So these activation functions are a mechanism to attempt to simulate that process of partial or differential activations at the postsynaptic site, right? So we had to differentiate it in some way. We knew that this one worked, but there's actually an interesting relationship here because neurons have two different sometimes many different versions of different neurotransmitters, right? One transmitter I might release for another neuron to pick up might be what's called excitatory, right? This is my positive promotion. Another one might be inhibitory, meaning that I'm gonna tell you, no, whoa, back off, red flag, right? Not only do I have the perspective to be able to detect a good positive, right? But I also have the perspective to be able to produce a good negative, right? Or a hard negative, right? So I can either excite or inhibit you. So if you think about this in perspective of weights, I can either add to the summation or I can take away from the summation. If we know that the activation of the subsequent neuron is going to be all of the activations times all of the weights relative to either yes votes, no votes, or null votes, right? So I can either choose to say yes, no, or I'm not participating. This is effectively a trinary system, right? We don't really have this in binary state systems because we don't really have a number that inhibits or sets a red flag or says, no, one in this system says, I have detected the pattern I want. 0 says, I didn't detect my pattern. -1 says, I detected another pattern that is literally mutually exclusive or antithetical, meaning it provides evidence of the inverse, right? It's evidence that it is not in my class, right? So it says, my class, not sure, totally not my class. And degrees of confidence within that. So the hyperbolic tangent function actually was one of the first. It was one of the first we utilized. It wasn't until later on that we actually implemented something along the lines of the shifted functions that we've been discussing. The ReLU is a solution for a problem with the linearity, okay? We said linearity, I'm going to punch forward to linearity real quick. Why is a linear activation kind of a problem? We don't necessarily have to deal with the activations as being probabilities, right? So there could be grades or degrees of activation. But what happens with a strict linear function? It's strong in both directions and continues to get stronger in both directions, right? So once you set the linearity, once you set this sort of tilt to the activation, any value that's on the positive side of the input becomes positively large, right? But also any value that's further from that value towards the bottom of the system becomes strongly negative. So we either have really strong activations or really strong inhibitions. What can happen with this is it makes the system possible for it to effectively equal one another out and cancel each other out. One neuron can either get so high in activation that it effectively mutes everybody else, or it can get so high in inhibition that it just completely makes the system not functional. All right, so the fix for that was something that we call ReLU, or rectified linear unit. Why we utilize this is because it is a piecewise function that allows for positive linear activations, but doesn't have the problems involved with inhibition. So, truly, an inhibitory network is kind of hard to work with, because rather than just having positive summations equaling forward towards the detection of outputs, you have neurons that are now responsible for detections of negative inputs. So there's some conservation of the data space, but also a lot of these weird little contributors that tend to look like naysayers, right? They're not contributing to the positive outputs, they're only contributing to the negative and inhibitory process. So it makes a chunk of the network effectively not participate in the learning process. It's only there to stop learning. It's only there to slow the learning process down, which we know that that's a good thing sometimes because we know that we have too much informational capacity, too much memory within the system as composed of all of the different weights and the recombination thereof being a mechanism for pattern storage. The potential for having strong positive activations made the system a little bit more balanced. This fixes something that we had with respect to these functions, because what's the maximum amount a particular neuron can activate to in this case? 1, right? Either 1, maximum output's 1. What's the maximum output here? There isn't one, right? So as the scale of the power of the input goes up, the power of the output goes up. So when we have these exceptionally high input features, these exceptionally strong features, we can have a strong activation. So this makes it to where when you have obvious stuff, the model can respond to obvious stuff. However, if it doesn't have the capacity to have a stronger activation relative to a stronger feature characteristic, if there's no linearity in the component of the increase in value for the output of the function, we can end up with something called saturation, right? The neuron learns up to a certain point, and then it's not able to learn anymore. It's not able to contribute anymore to the estimation of the system. This had problems with gradient offsets, and so we utilized something called a a leaky reloop, right? So this system is a rectified linear unit that happens to have a negative capacity to it. Effectively, it's two separate functions, two separate piecewise versions of functions. One increasing at one rate and the other decreasing at another rate, where some of the neurons, when you get stuck, right? So let's look at reloop previously. One problem with reloop is that weights effectively can die off. Effectively, once the model sort of gets saturated, gets desaturated to a certain point, the weight can get stuck back here in an offset such that it'll never activate again, right? It effectively gets stuck in a deactivated state. If you think about it this way, remember when we had the L1 regularization, the lasso? You remember how the lasso is incentivized towards trying to push the coefficients of the system down towards zero, right? When they weren't contributing highly to the weights. The error function here could push the activation output of the neuron to effectively zero. And it does so for a long enough period of time that neuron is no longer participating in the learning rate process, right?
So it effectively kills
It
it.
effectively kills it, it ablates it, right? So similar to the L1 regularization, ReLU suffers from that capacity of being able to totally deactivate connections in the neuron. Leaky ReLU attempts to fix that problem because it says problem is they can die, right? So ReLU can cause weight updates in a way that gradients can become zero. That's problematic. So we say the neuron will never activate again once that gradient for prop becomes zero because the output of the neuron is zero. So once it goes to zero and stops within the negative or within the low era of the ReLU, it's going to be propping back zero error because it has zero output, meaning it's not ever going to get weight updates anymore. How can you contribute when you have no weight? So the moment you go to zero, you die. It's true of neurons. It's true to neurons. Once they stop participating, once they stop being activated within neural networks in the brain, they die, right? So without input, the brain will die. This is a fix, like I said, just a fix for that relationship to add a certain amount of negativity so that it can slightly shift into the negative category once it gets towards zero, so that the system can pull it back up and out if it needs to later on, right? So even a small, weak negative value is still enough to cause the back propagation of error, which is still enough to cause the neuron to activate. So as long as the neuron is activating, it's still moving, it's still movable, right? It doesn't get stuck at zero. Yes?
Is there a reason why we seem to be using ramp functions instead of like a unit step function? Wouldn't that be able to give us some more flexibility
I've
in
seen
where we
those.
set it?
I've seen those. They're
Or are they not as
called
good?
healthy functions, I believe.
Oh, Calf.
Yeah, I'll have to
Whole
look at
new
it and see.
terminology.
No. This seems like a guy that just started them recently.
Oh, really?
It's
Okay.
their newer thing. So utilizing step functions would be grades of functions based upon unit activations.
Right.
You can model it in any way you want. You can model it as a complex nonlinearity, right?
Okay,
these
so we're
activations
just
can
using
become
this
these
for
activations can become complex nonlinearities. Why do we model them with simple functionalities?
For representation.
Computational.
Oh.
You can't.
Oh
do
yeah,
it,
that's right.
right. So these are easy.
Expensive
These are
computation.
it's computationally expensive because every single time I calculate the forward prop of the layer, I have to do what? I have to put it through this activation.
Right.
So I have to sum and activate. So every node gets one of these activations. So it's a complex function that I either have to model or update. Because guess what? These get updated too.
Right.
These functions can be modified. But when I look at it and say, complex nonlinearity, stepwise functions, whatever else, more pieces of the stepwise function create longer list tables, they create longer forward propagation. So these are all attempts to try to make this as simple as possible. If you guys are familiar with doing any kind of like board level programming or embedded systems design, it's kind of like how when you program a interrupt function, right? You want that interrupt operation to be like 1 op or 2 ops max.
Right.
Okay, that's the same argument here, is because this has to happen a lot. High frequency operation, you don't want it to be a complex op that has multiple steps in it because it's going to slow that forward prop operation down. And ultimately, it's going to make the final deployed model slow, which is not going to work. You want it to almost be instantaneous for the forward prop. Matter of fact, they figured out how to model some of this stuff in chips utilizing photonics. So these networks may actually be able to be constructed using photons or light speed transit in microscale electronics at some point in time. okay? So you develop a model, train it, optimize it, and then make a hardware version of it that runs with light channeling through a chip. So cool stuff coming out with that. But also these things can be accelerated as well. You can create an ASIC for this activation function, right? So you have an application circuit, so that you don't need to calculate that. You've got a section of the chip that actually does that calculation for you, okay? All right, so we talked about vanishing gradient. I think we understand what vanishing gradient is. Towards the back side of the system with lots and lots of nodes, all of them contributing based upon their weight scale, all of them getting back prop for their individual error. By the time you get back here, it's far enough back that you've already sort of offloaded the error to the local instantaneous versions. Because we know that most of the error should be closer to the region of origin, right? So the error would theoretically be most well adjusted by fixing integrations of feature characteristics. So it's the way in which we optimize based upon our features that implies quality of the model, right? So most of the error, we assume most of the error is going to be down here towards the beginning of the system, but you can fix this a little bit by saying, okay, I'm not going to give all of the error based upon the weights at this first layer. I'm going to say I have this many layers, so I'm going to try to keep some back, right? I'm going to try to force more to propagate across. So I can do like 70% here, then 80%, then 90%, in order to try to conserve more of the total value of error. We noticed that the summation of the deltas that go in for each of the functional activations of the nodes are the relationship of the product of the weight with respect to its assumed contribution to error. So if you don't have error to propagate back to the previous layer, right? You don't have error left over, you will end up with a gradient value that is so small by the time you back propagate it that there's nothing to update, right? There's only a smidgen, a little bit of dust left at the end of it to try to push those weights around. It becomes so small that in a digital computer you can't even adjust by that value, right? You're past the number of decimal places you have to actually change the value of the weight. So the weights at the very beginning of the system, they may initially be updated relatively well, but as time goes by, over time, they will eventually converge to values that are difficult to further update. We talk about early stopping, I think, a little bit, but the idea of early stopping is that with neural networks, they have the capacity to train far beyond what is acceptable. We watched one network whenever we were running through the neural training simulation, we watched it eventually go to effectively 0 for training error, because over and over again, by seeing different versions of the representation, what do you end up having? You end up with each batch, right? A batch is one subset of the overall training data. Each batch represents the mean and standard deviation for that local selection of the sample. So ultimately, over time, the system is going to what? It's going to eventually converge to the central limit of that system, the true underlying alpha of the original distribution. So as we're training up, essentially each one of those batches is kind of like a little fold, a little K fold in the system, right? But because I can only see a certain small amount of those at a time, I can't attempt to adjust my weights to compensate for all of them. But I'm attempting to adjust and fix the weights for this small individual example, assuming that that individual example is representative of the larger problem. So by this process of random selection and mini batching, I can create a stopgap for it being able to quickly converge to an overfit, and hopefully be able to create a point at which, if I stop it before I have significant divergence between the validation and the training set, I will have a model that, while still probably has more degrees of freedom than the true underlying problem, it's fixed now, right? It's not adapting any further. So if I stop it from learning after that point in time, I can actually deploy that network in order to solve that problem. And it will still only be a representation of the level of complexity that had been captured by what had been learned about the generalizable solution up to that point in time. So this is a cool trick that was sort of learned along the way, that if you stop it early, that the performance that you see here, where you have an agreement between the training and the validation data set, you're probably going to get maximum, sort of operational optimality. Notice still that the validation error is much higher than the training error. This is a common problem with complex spaces, all right? But the argument is that if I did as well as I could for training, and training was 70% of the distribution, that means that 70% of the likely samples in the future will fall close to the distribution of training, right? The argument is you make the model converge such that it minimizes training error without compromising validation error. That's a similar argument we made beforehand, but we typically tend to say, if I had to choose between training and validation, which one am I going to try to maximize performance on? It's going to be validation, right? But rarely would you ever have a circumstance in which, even within a neural network, in which training would not be better performing than validation, right? We're going to have to go into talking about some of this stuff next. I'm going to move forward through some of this and introduce an idea, and we'll come back to it at the beginning of our next time. But let me talk about dropout real quick. I'll spend 1 minute on this. Interestingly enough, a fully connected network, even though it seems like it has the maximum capacity for representation of information, sometimes has problems within it that the weights that might be seen or processed by certain nodes within the system are actually causing problems, right? So they may be due to confuser features, they may be due to odd gradient imbalance processes. So what we can do is we can utilize something like that ReLU function, right, or activation decay function, which can actually allow us to selectively eliminate individuals from the original fully connected network, right? So this is it's called a sparse network that is effectively masked for the original inputs. The advantage here is that this model can actually work around the ablation. So when a neuron is destroyed within a network, the data that it's relatively processing can actually be moved around by alternative systems. So I kill this neuron within the system, the information that it might have been processing previously is now going to be processed by these two neurons, right? These effectively take the burden of rerouting the load or rerouting the informational characteristics from the node that was eliminated in the system. This makes the network more efficient. It makes it slightly more robust because it can only see a certain amount of the feature information at any given time. Yeah.
Does that allow for reactivation later because it's changing how the interaction with that?
Nobody has ever been able to successfully prove that that does anything.
Oh, okay.
The weird part about it is if I turn that neuron back on afterwards, all of the value that it was previously processing has now been distributed to other nodes. So it would be hard for me to be able to calculate its gradient, right? Mm-hmm. So if it were activating positively in a forward direction where the error has already been propped to other nodes and balanced, then it's probably all going to seem like error because it's overemphasizing the feature. So once a network has learned and has reached a learning convergence, we say that its plasticity, its ability to remodel and balance the learning output, its plasticity has been eliminated, right? It becomes non-plastic once it has been ablated like this. Okay. So it's not flexible anymore, it makes it rigid.
Gotcha.
It's an interesting artifact of networks in general is that we have something called hypoctic learning, that they learn up to a certain point, and then afterwards they're really not capable of learning anything else unless you change the topic. It's like human brains, okay? It's similar to the way
can't teach an old dog new tricks.
Can't teach an old dog new tricks, that's true. It's very, very real likely that.
Well, thank God I'm not old yet. Or...
All right, we'll talk about, I'm going to talk about deep learning next time, but I want to introduce this basic concept to you. We've been talking about the natural, physical, continuous world, right? We also talk about feature extraction. This is the process by which we measure the natural world, and then we create quantifications. We put those into arrays, those become our data sets, right? What I choose to input from this natural space into the data set is, I'm biasing you, right? I'm telling you what I think is most important about this thing in order that you differentiate it. What's the limiting factor there? Since you can't go to the natural world to get your information, you rely on me to hopefully provide you with all the things about that particular target or individual or object, whatever it is, that would be necessary for more to be able to differentiate them from one another. So if you have a picture of a cat, you have a picture of a lion, right? How do I provide you with enough information such that you know exactly which features of those two images or those two objects differentiate them from one another? How high dimensionality is that input going to need to be in order to make that distinction? And the other portion of it is this is a real problem because we notice what that is. That's a person sitting at a desk doing a thing, right? That's a person we have to pay that has to spend their life doing this boring, mundane, menial task, right? So we said, we don't want that anymore. We wanted to try to figure out how to pass off this feature extraction step into the model. Since we know that it is taking information from the natural world and it is processing it and finding patterns within it, we said, hey, can we actually make this system a little deeper than it was previously? And now we can start having it get features, the relationship features, out of the original matrices of something like an image or input data sets. All right, so that's what deep learning is going to be. We'll discuss this on a day, probably our Monday on our way back. Be looking forward to this. And I think some of it's really cool. We do stuff like looking at image detection and object segmentation, convolution and the way in which convolutional neural networks work, and the way in which you find features or characteristics from image data processing in order to be able to construct higher level, what we call representations of that information, right? You don't know what a duck looks like. You can't tell me of any given picture of a duck, but you have an idea of what a duck is. That's a representation. It's a high level interpretation of the concept of a duck, right? So we're going to talk about how we can teach a system to learn high-level representations of complex objects and interactions such that it can describe them without having to have us tell it which features we think are most important. You guys have a great break. Thank you very much.
Thank you.
So the next week, is it off?
So what?
The next Monday?
We're off next week.
You come here and learn all you want next week.
I don't know.
We have what we call a fall break, Thanksgiving break.
Okay.
It is all of next week. So Monday, Wednesday, Friday, classes are next week. We'll be back the 27th, am I right?
Yes.
So we'll be back the 27th of November. And we'll have a remaining schedule. We're going to have 2 weeks of classes after that. So that's
6 classes remaining,
6
basically.
classes remaining. That means we have basically 2 classes a chapter for the remaining material, which is fine because I can do it. We'll get there.
Well, you can do it, but can I retain it? Can I absorb it?
I have no idea. You're trying to pour water on it when it's already wet.
It's just like
it's
running
just
off.
falling out.
Thank you.
Take care. Yes.